On this video, we'll be going over your related rates homework assignment. For the first problem, reading through, you notice that it is asking you to find dx dt. You're given a relation. So this one's pretty straightforward. You're just going to go ahead and find the derivative. Do remember that you find the derivative with respect to time because we are doing related rates. And do remember the derivative of 28 is 0. Now we're going to substitute in what we know. So we have 8 times negative 1. We're looking for dx dt plus 9, and we don't have a y value given to us, so we have to substitute in negative 1 to find that. So over to the side, we're going to have 4 times negative 1 squared plus 3y cubed equals 28. So we're going to have 3y cubed equals 24, and so it looks like y is going to be 2. We're also given dy. Dt is going to be 8, and all that equals 0. Now, you don't really have to multiply all of this out. You can just go through and subtract over this quantity and do some nice canceling here. So let's see what we're going to end up with. I would subtract this portion over to the other side, and then I'm going to divide by negative 8. So over here to the side, I'm going to have dx dt equals, and that's going to be negative 9 times 4 times 8 all over negative 8. And we can go ahead and do our canceling. So notice that our dx dt is going to be 36. All right, moving on to our next problem. Inside the problem, we see that we're going to have a circular area expanding. So right off, I know I need the area formula for a circle. And then we are told that that circular area is expanding at a rate of 10 millimeters per second. So I know dA dt, the rate of change of the area, is 10 millimeters squared per second. And we are told how fast is the radius of the wetted area expanding when its radius is 116 millimeters. So we want to know dr dt because we need to know how fast is that rate changing. So back over here with our geometric formula, we are going to find the derivative of both sides. So we're going to have 2 pi r and then dr dt. And now we're ready to do our substitution. dA dt we know is 10. 2 pi r, and we know r is 116 millimeters. And I'm looking for dr dt. And so again, dividing over 2 pi times 116. Notice we are not multiplying any of this out. That is so not necessary. And so reducing what we can, we see dr over dt is going to be equal to, and those will cancel, 5 over 116 pi. And then we need our units, and we can either work through those units or we can go back and look up in the problem, and we see it's going to be millimeters per second. Hey, our next problem, we're given a spherical balloon, and so that balloon is being inflated, so that is going to indicate volume. So our volume formula, and don't worry about having to learn these formulas, they'll be given to you. And so there's our volume. Now, labeling what we know from here, we're told that the radius of the balloon is increasing, so I know that is dr over dt, and that is increasing 1 over pi inches per second. Find the rate at which the volume is increasing, so I'm looking for dv dt, and we're looking for that when the radius is 1 inch. So as usual with all of these, we're going to have to go back to our geometric formula, and we're going to have to do the derivative. So dv dt equals, and that 3 is going to multiply down, so that's going to be 4 pi r squared dr over dt. And now we're ready to substitute in what we know. Again, we're still looking for dv dt equals 4 pi r squared. So r we were told was 1, so 1 squared times, and let's see, dr dt, and dr dt we were told was 1 over pi. So our volume dv dt is going to be equal to, those pi's are going to cancel, 4, and then our units, well, since we're talking about volume, that's going to be inches cubed per second. Okay, so for our next problem, we're told all the edges of a cube are expanding at a certain rate. So all the edges of a cube, so we need the volume of a cube, which is going to be just your side cubed. So we have, what are we told? So the edges of the cube are expanding at a rate, so that's going to be ds dt. So ds dt, the edges are expanding at 3 centimeters per second. How fast is the volume changing when each edge, so that's going to be a side, is 10 centimeters. So there's all of our given information. So we're going to go ahead and find the derivative of both sides again. And now after we find that derivative, we go and do our substitution. So we are looking for the volume for this one. So how fast is the volume changing? So we know we're looking for dv dt is going to be equal to, we had 3, our side squared, and then ds dt was also 3. So it looks like the rate of change of the volume is going to be 900 centimeters cubed per second. Okay, so for this problem, we have an aircraft that is climbing at a 30-degree angle to the horizontal, and we want to know how fast is the altitude changing if the speed is 500 miles per hour. So this problem can be set up with a triangle, I do believe. So we have our ground, and the plane is going at a 30-degree angle, and we want to know how, at what rate is the altitude changing. So we're really looking for this piece of information here, how that is changing. And I'm going to label that y, and this side length over here, I'm going to label that the distance, because that's how far the plane has traveled. Now it's important to label the hypotenuse, because how that side is changing is here with the speed. So from the problem, I see that dt is going to be 500 miles per hour. Now, from this other part, we need a geometric formula to set up, because we need to find dy dt. We need to know what is that rate of change there. So, given opposite and hypotenuse, we probably need to pick on the trig function sine. We're going to say sine of 30 is going to be y over d. And sine of 30 from the unit circle, we see that is going to be 1/2 equals y over d. I'm going to do some cross multiplying, so I have d equals 2 times y. And so from here we go ahead and we can do our derivative of both sides. So we have dt equals to dy dt. And keep in mind that dy dt is what we're looking for. We know the rate of change of the distance is 500 miles per hour equals to dy dt. So if we divide both sides by 2, we're going to have 250 in miles per hour. That's going to be the rate of change of the altitude. Okay, so for our next part, we have a 6 foot tall man is walking at a rate of 5 feet per second away from a lamp post that is 22 feet high. So I'm going to stop there and try to draw in what is going on. So there's our 22 foot lamp post. And we have a guy that is walking away from that lamp post at 5 feet per second. And let's see, so we're going to put that 6 foot tall guy somewhere about in here. And he's a really tall guy there. And we know he's walking away from that lamp post at a rate of 5 feet per second. So I'm going to call this part x. So his rate, dx dt, is going to be 5 feet per second. So, and we know he is 6 foot tall. And so at what rate is the length of his shadow changing when he is 60 feet from the lamppost? So keep in mind his shadow, so we must have a light source coming across. And so we end up with something that looks like this. And so we need to find this value over here. So we can call that value over there whatever. I'm just going to label it y, but you can label it whatever you want. So what we need to find from this is the rate that his shadow's in front of him. So really we need to find dy dt. That's what we're looking for. So what we're going to do with this, it looks like we're going to set up some proportions with this. And you've really got two triangles here. You've got a little triangle and a big triangle. The big triangle, I've got this side here and this side here. So that's going to be one side of it. And to find that total length of that base, it's going to be x plus y. And then I've got a smaller triangle on the inside that is this guy's height and that side length there. So we really have similar triangles here. So let's set up our proportion. We're going to say 22:6 equals, and then we're going to do this whole side length, so that's x plus y is to that one side length here, which is y. And now we have some kind of formula. I'm going to go ahead and cross multiply here. So I have 22y equals 6x plus 6y. I'm going to subtract our 6y over, so I have 16y equals 6x. I'm going to reduce by 2 just so that these numbers are a little bit smaller to work with. And now let's do the derivative of both sides. And notice once we do that derivative with respect to time, this problem works out to be really nice and neat because I know this value here. So let's go substitute in. We know dx dt is 5. So I'm going to have 8 times dy dx equals 3 times 5. So dy dx, or the rate of change of that shadow, is going to be 15/8 feet per second. Okay, so for our next problem, we're told that the height of a cylinder with a radius of 4 centimeters is increasing at a rate of 2 centimeters per minute Oh my, find the rate of change of the volume with respect to time when the height is at 10 centimeters. So one thing we definitely need here will be this volume formula, which is going to be pi r squared h. Now take note here, you're going to have to do the product rule with this, so be careful with that. You need that product rule. Alright, so let's see what else we have here. Let's go ahead and draw our cylinder, or I'll give it a good old try. Looks like some kind of bent can somewhere. So we have the cylinder, and we have a radius r, and then this height h. So there's our values. And now we're told that the height of the cylinder with a radius of 4 centimeters, so I know that radius is 4 centimeters, is increasing at a rate of, so notice what we have that is increasing here. We have the height of a cylinder increasing at a rate of, so dH dt is going to be 2 centimeters per minute. Find the rate of change of the volume, so dV dt, when the height, I don't know, when the height is 10 centimeters. Alright, so there's quite a bit of information there for sure. So let's see, now something for sure, now the height, it can change, but notice that the radius for this one, that radius is going to stay the same throughout. So I know r is constant here. That's not always the case. Now, with a cylinder it will be, but when we see a cone, it might not be. So we can go ahead in our volume problem, and we can go ahead before we do our derivative. We know r is going to be constant, and we're told that it is 4. So let's go ahead and substitute that in so we can stay away from that product rule. So that's going to be 16 pi h. Now we go ahead and we can find the rate of change of the volume. We're going to do the derivative of both sides. And we're going to go ahead and substitute in. So I have dV dt, which is what I'm looking for, is equal to 16 pi times the rate of change, which is going to be 2. So notice that volume is going to be 32 pi, and again, you're talking about volume, so it's centimeters cubed per minute. Okay, so for this one, we have a conical tank. It's 24 feet high and has a radius of 10 feet at the top. So before I read anything else, let's talk about what's going on here. So you've got a cone, and it's going to be inverted, and you're told that it has a radius of 10 feet at the top. Now that's important because if you have a conical water tank, so you're going to have something that looks like this. That's what's going on here. So if you notice, unlike the earlier problem with the cylinder, the radius and the height, they're both changing. So this part here, that's going to be your height. Here's going to be your radius. And inside of that, it's important to know, it looks like you've got a pretty good little triangle going on here. A nice little right triangle. That might be useful for us to know. So we have that conical shape. If water flows into the tank, so that's going to be a volume, and it's how that volume is changing because it's flowing into the tank, cubic feet per minute. So I know that's dV dt, 20 cubic feet per minute. How fast is the depth of the water increasing? So that's our dH. The depth of the water is the height. That's what I don't know. That's what I'm looking for. Increasing when the water is 16 feet deep. So that tells me that the height of the water is 16 feet deep. All right, so we also need the volume formula. So our volume is 1/3 pi r squared h. That's important for us to have, and that'll be given to you. So we really, we've got either our product rule, and then we're going to have to find the rate of change of our radius and our height, because both are changing, but they're both changing in proportion to each other. So we probably can set up some kind of relationship, because we're told that the entire conical, the height is 24 feet high with a radius of 10. So all the way at the top, we know that the radius is going to be 10 feet and the height is 24 feet. So again, we can set up a ratio here. We can say, well, our radius to our height is 10. So that relationship is going to be 10 to 24. And that'll reduce down to be 5/12. So we have the relationship R to H is 5/12. We're wanting to just find dH dt. So let's solve all of this for R. So I'm going to multiply our H over. So I know R is equal to 5/12 H. Now this is quite a bit of work here, but it's either you're going to do a lot of work at the beginning or the end. There's no way to avoid it. So what we're going to do with this value is we're going to go back and plug in to our original formula. So I'm going to come all the way back over here to the beginning, and I'm going to say, well, that's 1/3 pi, but in place of R, I'm going to put this value here, because we know that relationship. And if we square that, that's going to be 25/144 h squared, and then times h. And let's see, what can we do with that? My goodness, I would not do anything with the 1/3. I would just keep bringing that through. And so I know that's times 25/144, and that's going to be h cubed. We are finally to the part where we can do our derivative. Finally, we're almost finished with the problem. And yes, all of these problems are about this long. All right, so dv dt equals, when I multiply that 3 down, that's going to cancel out that 1/3. So I'm going to have pi. Remember, 25/144 is just part of the coefficient. And then we're going to have h squared dh dt. Now we get to plug in. My gracious, this is the never-ending problem. So I'm going to change colors when we plug in, so trying to keep from all of this from running together. So here we're going to plug in. So dv dt we saw was 20 equals, and we've got pi. Let's go ahead and just say that's 25 pi over 144, and then h squared is going to be 16 squared, and then dh dt. And finally, we're going to divide all that mess over. My gracious, it is the never-ending problem. So we are going to divide all this over. And I guess we need to do, since we've got a fraction, we multiply by the reciprocal. So when I move this over, I'm going to have 144 on top times 20 over, and let's see, in the bottom it's going to be 25 pi times 16 squared. So I'm going to throw in that 16 squared. And that's going to be dh dt. And then from there, we would need to go through and do some simplifying, if we can, to get to that final answer. Let's see what we can simplify here. Let's see, 20 and 25, those will simplify. You've got a 4 up here and a 5 down here. let's see, is there anything else? Well, 4 and one of those 16s, oh my gosh, what a mess. If you keep simplifying down, it looks like dHdt, and I'm going to confess, I'm going to throw it in the calculator. And that's going to end up being 9 over 20 pi. And I'm doing that because I am out of room on the screen, folks. Alright, so we have these two ladies, and they're driving to a wedding. How sweet of them. And so we have one lady that is driving at a rate of 50 miles per hour, and she's going east. So we're going to call Miss E. She is going east here. Alright, and she is going 50 miles per hour. And let's go ahead and just call this side X. And so I know that value is going to be dx over dt. And then we have a Miss A, and she is driving south toward the wedding. And we know that she is going, and we're going to call this Y. We're going to call it dy dt. And she's driving 38 miles per hour. At what rate is the distance between the two cars changing when, I don't know, Miss E is 1 mile. Okay, so we know here is 1 mile. And Miss A is 3/4 mile. So I know this side over here is going to be 3/4. From the wedding. So we're just going to call that right angle the wedding. So I want to know the rate of change of this side here. Alright, so that looks like a good old Pythagorean theorem problem. Now we do need to find this side over here, this side z. So let's go ahead and plug into our Pythagorean theorem. Remember that's x squared plus y squared. And in this case we're going to call that z squared. And so we're going to have 1 squared plus 3/4 squared equals our missing side squared. So we have 1 plus 9/16 equals z squared. And so that's going to be 25 over 16. And we need the square root of that. So we're going to have 5 over 4 as that side z. So we know 5 over 4. But also keep in mind we are looking for the rate of change of the distance between the cars. Alright, so we also need our Pythagorean theorem, and we need to do the derivative of it. So we're going to pull this down over here. Let's go ahead and do the derivative. So we're going to have 2x dx dt plus 2y dy dt equals 2z and then dz dt, and that's what we're looking for. So we can go ahead and drop a 2 from all of those since it's in every term. And we know that the side length is 1. The rate of change is 50 plus, and the side length y is 3/4, and the rate of change is 38. And then we know side z is 5 over 4, but we don't know the rate of change. That's what we're looking for. Alright, so we have 50 plus, and let's go ahead and cancel that 4 into 38. So we really have 50 plus, and that's going to be 57 over 2. And all of that's equal to 5/4 dz dt. Okay, and so putting this together, 50, well I'm going to change that to be 100 over 2, isn't it? If we got a common denominator. So that's going to be 157 over 2 equals 5/4 dz dt. And then we need to multiply by the reciprocal there. So we're going to flip that over. And so it looks like we're going to have 157 over 2 times 4 over 5. And so let's see, we're going to have 1, 2, so dz dt is going to be equal to, and gosh, if we multiply that by 2, we're going to have 314 over 5. And that would be miles per hour. All right, so, And looking back up at the problem, keep in mind this distance here is shrinking, because as they get closer and closer to each other, closer and closer to the wedding, I should say, that distance is shrinking. So we need to go ahead and just make that, it's going to end up being a negative value. And again, that's going to come from us realizing what's going on in the problem. And that's because that distance is shrinking, so the rate must be negative. Okay, so for this one, we have a hot air balloon, and it is raising at a rate of 8 feet per second from a point on the ground, 60 feet from an observer. Find the rate of change of the angle of elevation when the balloon is 25 feet above the ground. All right, so let's see if we can't draw us a good picture of what's going on here. So it's probably going to be some kind of triangle. And an angle of elevation, you're looking up. And let's see, find the rate of change of the angle of elevation. So we're not going to know what that angle is just yet. And let's see, we know if we have an observer standing here somewhere, draw my little stick person, and so that hot air balloon is rising from the ground, so it's shooting up this way. And let's see, it's gonna be a nice little, that's the best I got for hot air balloon. That looks pitiful, but oh well. So okay, it's gonna bother me, I gotta change it, sorry. So we have a hot air balloon. Let's see if we can make the basket look a little bit better, maybe. Give up. All right, so, well, normally that's going to be X. This side's going to be Y, and this side over here, we're going to call that Z. And let's see, I know this side length here, the observer is standing 60 feet away. And what else do I know about this? Find the rate of change of the angle of elevation when the balloon is 25 feet off the ground. So I know over here is 25 feet. All right, so we need to find the rate of change of the angle. So we're going to have to do some kind of trick. And one thing for sure, we know this side length's not changing. And this side length is changing. We were not given anything about this other side length. We don't know a whole lot about it. So why don't we use this side that's going to be opposite and this side that's going to be adjacent, which means we probably need to use tangent of theta. And we know tangent of theta is going to be y over 60. Okay, now don't put, we can say 25 over 60, but we need to have something there that we can do the derivative of. And we know something hopefully about the balloon is rising, right? 8 feet per second. So I know the rate of change for the side Y. All right, so this, let's go ahead and rewrite it to be tangent of theta equals, and let's go ahead and pull that 60 out to the side because it looks a little more friendly and you're not tempted to do the quotient rule here. All right, so tangent, the derivative of tangent of theta, that's going to be our secant squared of theta. And then we're going to say d theta dt. Don't forget about taking the derivative of that angle. Equals 1 over 60 dy dt. All right, so now we've got some other stuff we've got to find. Well, let's see. Y is going to be 25. And so we can find this side length here, because remember secant, that's going to be secant theta all squared d theta dt. And so that's a value we should be able to find. And we know dy dt is 8, so I'm going to go ahead and plug that in. So if we knew this value, which is going to be hypotenuse over adjacent, then we would be in good shape. So let's go ahead and draw our triangle again. And we know this side is stuck at 60. And we're wanting to know what's going on when this side is 25. So we can use our Pythagorean theorem and go through, and we will find that this side over here is going to be 65. Now I cheated a little bit because I saw that was 5, that was 12. So this side over here has to be 13. It's a Pythagorean triple. And so that's going to help us on this. Or you can go through the Pythagorean theorem, either one. And also 3, 4, 5 is another handy Pythagorean triple. And so we're going to do hypotenuse, and I'm going to use the reduced form. So we're going to have hypotenuse over adjacent, so that's going to be 13 over 12 all squared d theta dt equals 8 over 60. And so now our next step, we need to divide over our 13 over 12 squared. I'm going to mark that out and put it over here. And let's see, I'm going to square it, and that's going to be 144 over 169. And so when we go through all the reducing process, we should get 96 over 845. And the units here, if it's the angle changing, it's going to be radians per second.